Let us analyze the four cases shown via the method of intuition as well as the method of constraint motion. So here the angle of the wedge is theta. Here the angle of the wedge is particularly given to be 53 degrees and 37 degrees. So this forms the 3, 4, 5 triangle. That should be known. So here the angle of the wedge is again theta, and here the angle of the wedge is theta. So using the method of intuition, in the first diagram we can understand that if the acceleration of mass m2 is a in the downward direction, then the acceleration of mass m1 will be a along the upward direction of the slope. So both the accelerations happen to be a. So using the method of intuition, we can write down the equations m2g minus t is equal to m2a and t minus m1g sine theta, because m1g sine theta is the component of the force of gravity. The force of gravity is m1g in the downward direction, and its component along the plane happens to be m1g sine theta. So this component happens to be equal to m1g sine theta, and perpendicular to the plane, if the force of gravity is resolved, then the perpendicular component happens to be m1g cos theta. So this is m1g sine theta, and perpendicular to the plane it is m1g cos theta. So these two equations will give us the correct answer as far as the acceleration and the tension is concerned. So if the same problem were to be solved using constraint motion, then we would assume this length to be equal to x1 and this length to be equal to x2 without taking the circumference length of the pulley, because that is a constant and gets differentiated out to be 0. So this length is x1 and this length is x2. So using constraint motions equations, we can write x1 plus x2 is the length of the single string that is present over here. In that case, we would have to assume the acceleration of mass m1 to be down the slope and acceleration of mass m2 to be in the shown downward direction. So after differentiating x1 and x2, we get double differentiating, we get a1 plus a2 is equal to 0. So this is one equation, and while using constraint motion equations, the other two equations that we can write down from Newtonian dynamics are m2g minus t is equal to m2 a2 and m1g sine theta minus t is equal to m1 a1. So this is the analysis of the first diagram. So let us say we want to do the analysis of the second diagram. Then in that case, let us do the intuition based analysis. The intuition based analysis entails, let us assume that the mass m1 is going up with acceleration a, then the mass m2 will be going down with acceleration a. Even if our assumption is wrong, then we'll get a negative value of acceleration a, which is perfectly fine. So we can write down m2g sine 37. Sine 37 happens to be 3 by 5, which should be known to the listener. So m2g sine 37 minus t is equal to m2a. Similarly, t minus m1g sine 53 is going to be equal to m1a. So using these two equations, you can find out the expression and the value for acceleration as well as tension. Now if we do employ the method of constraint motion, then in that case we would have to take this particular distance as x2 and this particular distance as x1. Ignoring the circumference length of the pulley, which gets differentiated out to be 0, we can now write down the constraint motion relationship equation for the string to be as follows: x1, so this length happens to be x1 and this length happens to be x2. So x1 plus x2 is equal to the length of the string. In such a case, we would have to assume the acceleration of m1 to be a1 down the plane, acceleration of m2 to be a2 down the plane. After double differentiating this equation, we get a1 plus a2 is equal to 0. So this is the first equation that we have obtained using the method of constraint motion. So for the next equation, we can write down m2g sine 37 minus t is equal to m2 a2. This is the second equation, and m1g sine 53 minus t is equal to m1 a1. So using these three equations also we can solve this particular system. So let us move to the next diagram and its analysis. So in this particular case, we'll directly employ the method of constraint motion. Here, this particular distance is assumed to be x1. So this distance is assumed to be x2 from the pulley P1 till the pulley P2. This distance is also assumed to be x2. The mass m2 is rigidly connected to the pulley P2. Because of that, what happens is the acceleration of pulley P2 is going to be the same as the acceleration of mass m2. Hence, we can write down the length of the string to be constant. Also, while writing that down, we realize that this particular distance d happens to be a constant. So the length of the string that passes over both the pulleys is nothing but x1 plus 2x2 plus d. This happens to be the length of the string. If you double differentiate this, then we get a1 plus 2a2 equal to 0. So this particular equation is the constraint motion relationship between the two accelerations. Also, if the tension in the string is going to be T, then the tension in the string that connects M2 is going to be 2T, because the pulley P2 will have a net zero force acting upon it. So in such a case, the other two equations will be, so the acceleration of M1 has to be assumed going away from the rigid support, and M2 also I am assuming going away from the rigid support. Both can be assumed to be going away from the rigid support, or both can be assumed to be coming towards the rigid support. As a matter of convention, for ease of problem solving, I am assuming both to be going away from the rigid support. So for the mass m1, we can write m1g sine theta minus t is equal to m1a1, and for the mass m2, we can write m2g minus 2t is equal to m2a2. So these three equations are going to give us the solution for accelerations a1, a2 and t. There is a way in which this particular question can be done intuitively as well. I will leave it to the imagination of the listener as to how to do it intuitively. So please note the fact that this d happens to be the constant length of the string that is not moving. So this upper rigid support is actually, you could have drawn this upper rigid support at this level also, because the length of the string d, that is the length from the upper rigid support to the center of pulley P1, remains constant in this particular question. This is something to be realized via physical intuition. Now, in the next diagram, we would like to employ the method of constrained motion, and we would say that this length is x1. Mind you, in this particular diagram, let us say this is mass m1 and this mass m, this I am labeling as mass m2. So this slant length is x2. So the length of the string happens to be x1 plus x2. This is equal to the length of the string. Alright. So if we do differentiate this equation, then we get, double differentiating this equation, we get a1 plus a2 is equal to 0. Here we have got a movable wedge. So this wedge can move towards the right or the left. It is not a fixed wedge, unlike the other three cases shown. This is a movable wedge. So since the wedge can move towards the left or right, the distance of the wedge from the rigid support, which is the left hand side wall, has to be taken as a variable distance. So the mass of the wedge I am assuming to be m1. In any particular question, the mass of the wedge will usually be given. So this wedge is moving towards the left hand side as the mass m2 is moving downwards. This is what is intuitively happening over here. So a1 plus a2 is 0. Now in order to write down the equation of the mass m that is sitting on top of the wedge m1, it is important for us to also sit on top of the wedge m1. Now if we do that, then in such a case we will get a pseudo force because we would be in an accelerated reference frame. So in such a reference frame, we would get a pseudo force that is applied on the mass m. So let us assume that the acceleration a1 is the acceleration of the wedge m1 towards the left hand side. Then the pseudo force that will be applied on mass m will be towards the right hand side and will be equal to mass m into a1. So this pseudo force will have a downward component which will be ma1 cos theta. So mg will also have a downward component. So the equation that needs to be written is mg sin theta, the downward component of mg, plus m a1 cos theta. So this is the net downward component of force minus t. This is the upward along the inclined component of force. This is going to result into m into a2, where a2 is the acceleration of m down the plane. So this is a2. So this is the Newtonian dynamical equation for the mass m2. Even if at this point in time the listener would not possibly understand this particular equation because of being non-familiar with the concept of pseudo force and how to use it in Newtonian dynamics, in that case I implore the listener to only focus upon the constrained motion equation, which is a1 plus a2 is equal to 0. Now the next equation is to be written for the mass m1. So the mass m1 is moving towards the left hand side with acceleration a1. So this mass m1 has a normal reaction that is being applied to it because of the mass m2. So this is the normal reaction. This angle is theta. So this component of normal reaction happens to be n sin theta. So there is this component of tension also acting, and there is this component of tension acting. So since this angle is theta, since this particular angle is theta, then according to alternate angles, this particular angle is also going to be theta. So this is theta and then this is theta. So since this is theta, the component of tension towards the left hand side will be t cos theta. Towards the right hand side rather will be t cos theta, and towards the left hand side it will be t. So t minus t cos theta plus n sine theta, this will be equal to m1 a1. So here the unknowns are a1, a2 and t. Everything else is known. So there is this n also, that is also an unknown. So we can write down the perpendicular direction equation for the mass m and find out the value of n. So basically the n force is acting over here. So n plus ma sine theta is going to be equal to mg cos theta. So mg cos theta will be balanced out by n plus ma sine theta. So this will be equal to mg cos theta. So this is the equation, that is the perpendicular direction equation as far as the mass small m that is kept on the movable wedge is concerned. So the force dynamical equations are 1, 2, 3, and the constrained motion equation is a1 plus a2 happens to be 0. So we have got 4 equations and the unknowns are t, n, a1 and a2. a2 happens to be the acceleration of mass m with respect to the mass m1 down the plane. a1 happens to be the leftward acceleration of mass m1. So we have employed the concept of pseudo force over here. So readers who are not familiar, listeners who are not familiar with the concept of pseudo force may ignore the concept as of now and just focus upon the constraint motion relation for which this problem is being stated in order to illustrate this particular constraint motion relation, which is a1 plus a2 equal to 0. So the other equations will be understood when the concept of pseudo force is well understood by the listener.